Thank you, Gutierrez, for the invitation. First of all, it's nice to talk again, even though virtually this time. Given the vibe you gave me just now, I'm going to share the CrunchDAO link in the chat. So I'm going to talk a bit about where I'm from, let's say, where this works is coming from. These works are coming from. Actually, this is a follow-up of a work we had the opportunity to present in Abu Dhabi Machine Learning last month. And in some sense, it's a reply to the main criticism that we already saw coming, but that was explicitly coming out in that occasion. So first, before getting into the math and the technicalities of the problem at hand, CrunchDAO is about using Web3 technology. So it's a decentralized autonomous organization to put together data scientists and quant to build models, to build supervised learning models, basically, on data sets associated with the financial market, and more particularly on the US stock market. Please interrupt me and write questions. I don't know what's the format on Zoom, but I should be able to see. If there are questions, please throw them in while I'm talking, please.
Yes, yes, we'll go through them at the end of the talk.
Okay, yeah, right.
That you have, a clear shot to express yourself, and then we'll take the questions. Right.
So CrunchDAO is a decentralized research team, basically, of data scientists and quant working on financial data to predict the market. And so it's a way of crowdsourcing alpha, crowdsourcing investment strategies, with the goal of basically solving with this ensemble technique the variance bias trade-off. So being able to ensemble many predictions. And I think the best way to think about ensemble learning is that in a highly noisy space, there are many ways to be wrong, to be correlated and wrong. And there's only one way to be correlated and right. And so if you average out things, noise cancel each other. This is the intuitive way of thinking about it. While the signal reinforces. And so that's why, for example, in boosting techniques, but also in simple ensemble averages, the ensemble can be stronger than the strongest individual signal that contributes to that ensemble signal. So in this context, and I encourage everyone to participate in the tournament. So it's a crowdsourcing investment strategies using tournaments. Which happen every week. In this context, we have to make clear design choices on the data set and on then the financial product that we can then propose coming out of this investment strategy technique. One of the requirements is that and I won't bother you with the technicalities of the abstract, but the idea is that we want a portfolio which is neutral to some risk factor. What is a risk factor? You can think of this more in machine learning language. You can think that there is a sparse basis that can capture the majority of the movement of the stock market. So there's a old model, relatively old model, the CAPM, in which there is this beta quantity that already captures a lot of the movement of the stock prices. So you can think of this as the performance of an individual stock over a market index like the S&P 500. So there is this macro variable, so it's called a factor, that captures a lot of the information of the actual individual returns of all the stocks. And so all the stocks can be represented by a linear component, which is the exposure to this factor, plus something else, which is a residual, which is much smaller than what's explained by the factor model. And you can have this for multiple factors. You can have a multi-factor model in which you have, 2,000 objects, 2,000 stocks, and 2,000 variables. But actually, their behavior is pretty much captured by a sparse basis compared to the number of stocks. So let's say 20. And so one way to be able to crowdsource alpha in this context is to orthogonalize the features. So basically to inform the data set seen by machine learning models about the necessity of the prediction to be orthogonal to such risk model. So I won't bother you, I guess, with these financial details, but let's say we start from this geometric perspective in which we have this feature matrix X, which is a cross-sectional representation of the state of the system. Yeah, we have a number of features and a number of particles, let's say, a number of realizations of the system. And so for each cross-section, for each timestamp, for each moon, epoch, whatever you call it, you represent the system by this matrix X. Associated to it, you have a matrix that represents the exposure of all the stocks participating in X. Their exposure in that cross-section to a set of risk factors. And so this matrix B comes out. And finally, you can have a vector target, which is some kind of risk-adjusted return to be predicted, so the future behavior of the system. And in general, let's say the feature space can be non-orthogonal to the risk model. And so you have the first condition. Also, let's say that the second condition about the fact that the covariance matrix of the feature is the identity. You can do transformations that reduce some degree of correlation with the physical information you capture. But you can arrive at a point in which that condition is realized. So you have features which, in the space that they define, they're orthogonal to each other. You can also do transformation on such features such that this representation of the system is orthogonal to the risk model as well. So you can orthogonalize all the features to all the factors. And you can make the first condition to be orthogonal. And this is a choice that one can make to make the output of models built on these features orthogonal to B. But it could be restrictive. Also, as I said, Y is a target which is residualized against some risk factor. So by design, let's say Y is orthogonal to B, and it's the last equation here. Now, there is this interesting fact. I mean, pretty interesting to me. I here put a blog post by TransiTAO, the famous mathematician, talking about the transitivity of correlation. And the idea is pretty easy, actually, when you think about it, but it's not intuitive. You can have two vectors which are strongly correlated with each other. Sorry, three vectors, A, B, C, let's say, A and B strongly correlated, B and C strongly correlated. But it can happen that A and C are orthogonal, so zero correlated. So orthogonal with respect to the inner product defined by the correlation. And so if I go back to the original slide, let's say we can impose X to be orthogonal to B, Y is orthogonal to B. But even if we build a prediction that leads to having a Y hat, an estimation of Y, which is strongly correlated with Y, this doesn't imply at all that this prediction is orthogonal to B. This is true, and this example by TransiTAO shows it for a 45-degree angle, basically. You know, you have the X, the vector on the X-axis, the vector of 45 degrees, and the vector on the Y-axis. And so the correlation here is 50%. This is not at all true. I mean, this condition happens if the correlation is 50%, let alone we could try to imagine how more difficult it would be for the transitivity to happen in a much higher dimensional space in which the correlation is not 50%, but it's like a few percent. So this is the problem we try to see geometrically. And to solve this in this work, we propose to use we start from linear regression at least, which is a fairly simple supervised learning technique. It's a least square with a rigid regularization. And the idea is basically that we want to get an estimate of Y, which minimizes the squared error compared to the target Y. And it's the first component of this fitness function, which is a function of a set of parameters. So the linear coefficients combining the features in your data set. So you want to find a set of lambdas that minimizes this squared error. But at the same time, there's this relaxation that for C equals 0 leads to the normal least square. But for C higher than 0, it's basically telling you, it's basically, and I show, yeah, you see it in the solution actually, it's adding some, a constant to the diagonal element of this matrix. And so it's a relaxation on the behavior of the lambdas about their sparsity in a square sense. Anyway, you can do linear algebra. Everything is linear. And so you can set up this estimation and say, if X is orthogonal to B, I'm sure that this prediction will be pretty orthogonal, actually exactly orthogonal to B, because this is lambda is going to lead to a linear combination of X's. So there's an analytic solution. The idea is, let's assume that X is not orthogonal to B. Can we redesign the fitness function of the ridge regression such that we incorporate in it the constraint, the information about the prediction being orthogonal to the risk model while being strongly correlated, let's say, with the target? Yes, we can easily. We can just add a term to the, sorry, I don't know if you see my face here. Let me move it. We can easily do it by adding a term to the fitness function. Again, we stay in this ridge regression context that allows the model to generalize out of sample, let's say, not overfit. This is the main idea of ridge regression. We can add to these two terms, one which is this term, which is telling me that again in a square sense, so that we can solve it with least squares. The exposure, so the component of the prediction y hat, which is x lambda, the inner product with B is small. So the projection, thinking of it geometrically, the projection of y hat on the hyperplane spanned by the basis of B is small, and the correlation of y hat with y is high, and you see it here. Now this is linear and still interesting because X can be non-orthogonal to B. But let's say we want to use this machinery in a nonlinear context. We want to build nonlinear models, being able at the same time to be correlated with Y and be orthogonal. We can kernelize this fitness function. We can kernelize we can use kernel ridge regression with this modification of the additional term in the fitness function. So I don't know if there is value in introducing kernels, but the idea is basically that the value is that, let's say the mathematical value is in what's called the kernel trick, which allows you to compute inner products in a space, in a Hilbert space, more technically, in which the metric is nonlinear. So the distances are measured. Yeah, it's the map from Euclidean space to Hilbert space is nonlinear. Therefore, you are able to use linear algebra in this mapped space, linear techniques, just applying this kernel. And you don't even have to explicitly define the function that brings you from Euclidean space to Hilbert space, but you just have to define how the inner product looks. So how these distances between mapped points from Euclidean space to Hilbert space, how it looks. And so the idea is that, for example, if you look at this kernel, this gram matrix, which is basically the matrix of the inner products in the component of the X matrix, if the kernel is linear, basically you get something like the transpose of the covariance matrix. And as I said, the covariance is diagonal, so you see that here we don't have much information. While if you use a nonlinear kernel and you get the radial basis function as an example, you get a gram matrix which is much more structured. So actually we tried briefly last week to look at this in terms of information theory and to try to say something about the optimal kernel from the entropy of the gram matrix. So let's say thinking about the optimal kernel in terms of information theory. Anyway, you see that if you put the lenses of nonlinearity, some structure could emerge. So this is the lesson learned from this slide. I won't go into the detail of the derivation, but basically you can use this kernel trick when you move from a dot product, so a linear dot product. You move from this to an inner product that you don't need to define explicitly, in the sense that you just need to, as I said, use the kernel trick and define the function that talks about the relation between points, and not how points move from Euclidean observed space to this Hilbert space. So this is the derivation, is just linear algebra, to be honest, beside this kernel trick that you see applied from equation 11 to equation 12. So nothing too fancy. Then we want to find the optimal solution for this. We want to find the minimum of this function. So we compute the gradient. And but yeah, at the end you get something which looks like a least square solution. You see, in place of the X matrix, we have the gram matrix, in which, as I said, we have computed the kernel. So the nonlinearity appears implicitly in this K matrix here. Again, we have the ridge regularization here, and then we have some matrix multiplication here about the factor exposure. So you see that we have an extra parameter here, and if we want to set D to 0, we go back to kernel ridge regression. If we want to set the kernel to linear, we go back to and D equal to 0, we are back to linear ridge regression. And again, if we bring down even C to 0, we have least square. So I hope it's clear that it's pretty incremental and nothing, no discontinuity in the reasoning. But still, this is powerful because we can get an optimal set of R that give us a linear combination in this mapped space, and therefore define a nonlinear function in the space we started from. So we can build a nonlinear model on X to predict Y, such that we are orthogonal. And we are orthogonal not in Hilbert space, but we're orthogonal where we need to be orthogonal. And so this is what we get. So yeah, I would say, yeah, let's go straight into the results. So how did we test these things? We trained the models in some window, time window, so a set of moons, a set of epochs. Maybe let me add something which I didn't put in the slides, but because we are interested in doing machine learning on, it's not really a time series problem, but yes, it's not explicitly a time series problem. I set it up as a regression problem, but still we are interested in being able to predict future behavior. And so there are two interesting things that are compatible with this format. The first is that we can perform batch least square. So we can generalize this to a batch of samples, and a batch is a matrix X. So we can basically put down, we can increase the size of X to be same number of columns, number of features, but then the number of rows is number of stocks times number of moons. And so we can set up this batch least square. Moreover, and this is interesting for the time series aspect of the problem, we can use weighted least square, and we can add to this formalization a weight that tells us that in this batched optimization, it's more important to be optimal in the last moons compared to the first ones. To make an analogy in finance, for example, when one is interested in computing covariance matrices, it's common practice, let's say, to go in line with the fact that volatility calls volatility. So the volatility of time series in financial markets are non-stationary. Therefore, there is some memory in play. Therefore, to compute it, you take the time series, but you weight exponentially. You weight it in some nonlinear way, and you say, well, if volatility is close to me, this is, even if let's say it was flat before all the way, this is my estimation of the current volatility is higher than if the volatility was 1 week ago, because there's this memory effect. So in the same way, because we're interested in predicting, we could say, well, let's build a linear model that puts more weight on the last months, because we believe there's some kind of memory in the system. And because the kernelization doesn't change the linear nature of the formalism, we can set up easily this weighted scheme. Anyway, this we didn't do. We just investigated the behavior in sample on a batch of 25 months, and we assessed the performance out of sample. To be honest, we didn't spend enough time, because we didn't have it, on digging into these choices. Let's say these hyperparameter choices. For example, we have a training set which is smaller than the test set, but we really wanted to push out the generalizability of the model. Anyway, we did various experiments, and we investigated starting from an X which is already orthogonal, looking into D equal to 0 or D bigger than 0, and then looking at different kernels. So linear kernel, which leads back to linear regression, and radial basis function kernel. In any case, as I said at the beginning, we know that Y is orthogonal to B, so Y hat, even if it's not orthogonal, the amount of information we are interested in Y hat is the component orthogonalized against B. So even if the training model, the model trained doesn't know about the fact that Y hat has to be orthogonal, still to assess its value, we need to look at it post-orthogonalization. So let's say offline, let's say there's online orthogonalization, which is the one performed during training. Then offline orthogonalization, we do it once we get this Y hat and we see how good it is. So yeah, this is starting from orthogonal features and the linear constraint model. And constrained, I mean D equals 0, so no need to push for orthogonality. Actually, we saw, which is pretty trivial to show that, if D is bigger than 0 in the case of orthogonal features, the result is equivalent, because the model, and if the model is linear, because of course the model cannot load on factors if the features are not exposed, and if the model is linear. Even with nonlinear, actually, with orthogonal features, I don't think I'm showing it here, but even with orthogonal features, if the model is nonlinear, because Y is orthogonal to B, the Y hat is not that correlated to B, but it's still a non-negligible amount of correlation is captured. So even in a context in which X is orthogonalized against B, there is value in imposing this additional cost in the fitness function. So this is an information coefficient rolling Spearman correlation on this year, basically 50 weeks on 2017. And yeah, you see that the average is around 0.8% Spearman correlation. While if we set up the nonlinear model, we have a slight boost. Unfortunately, I was negatively surprised by how little the improvement was, but I mean, in percentage is not as small. Using this nonlinear constraint model on non-orthogonal features. As I said, we showed also the result on orthogonal features nonlinear model. And in that context, also constraining the fitness provided a benefit, because the model loaded on factors. So there are clearly next steps that we have to perform on this, let's say, on testing this methodology that has value by itself, but has to be tested against a few experiments. So first of all, we didn't tune that much hyperparameters. There is this problem as soon as you go nonlinear that you can overfit. So we have D, we have C in the fitness function, but we also have gamma, which tells us, in the context of a radial basis function, that tells us basically how sparse the Gram matrix has to be. So how important non-local interactions are in the context of RBF in particular. But yeah, you can tweak the kernel. Is the same concept of, in some sense, training a neural network. You have to fine-tune the other parameters such that your model performs well out of sample. So it generalizes well, doesn't overfit. And so for this, the natural choice is some kind of grid search in the hyperparameter space which is performed on cross validation to assess the optimal hyperparameter. Then yeah, we can expand the window here. I didn't do it, I guess. We are just training once on a window, and then we are evaluating, so testing on an expanding window. Sorry. Then yeah, weighted square, I mentioned it, and yeah, the inference, it's a bit tricky in the sense that there's value in looking into it. The fact that if you perform batch estimation, when you move your window, you already have knowledge of partial knowledge of the target because it are the targets from the previous moons. So you can combine in the Bayesian context the knowledge of the model and the knowledge of the observed partial observations of your target. Finally, confidential computing. Well, I guess there's not much value in going into it. Everything started from the need for us to be able to let participants in the tournament orthogonalize against factors that they cannot see, but still be able to propose a well-posed problem, let's say, in which people in the tournament can aim at performing well, so that there is an alignment of interest between the fitness function of the tournament and the objective of the DAO as a whole. But we cannot share all the data, so there are interesting solutions from encryption that we're looking into it, but I won't say more about this today, I guess. So close here, and I'll show you a mid-journey picture of me asking, I don't remember what, but like an orthogonal vector in Hilbert space that captures, I hope, pretty well the idea around this work. Thank you.